Well, hello to everyone. I'm America Califano. I'm a postdoc research associate from the University of Salerno in the south of Italy. And today I'm going to show you our very preliminary results about the fatigue performance of specimens made in aluminum silicon magnesium alloy obtained by selective laser melting and subjected to both constant and variable amplitude fatigue loadings. Well, first of all, I will briefly introduce the topic, then I will focus on the methodology that is usually used when tackling the issue of variable amplitude fatigue. I will briefly explain the experimental tests that were carried out at the University of Salerno, and then I will show you the preliminary results and wrap up with the final conclusions. Well, I'm not going to repeat things that we all know, but I just would like to underline that aluminum alloys are quite common in several fields, especially in the automotive field where oscillating loads are quite common. These kind of alloys, like for example, the aluminum silicon magnesium 1, are characterized by several positive aspects, like for example, high strength rather than impressive corrosion resistance. But in particular, the powder of this kind of alloy is characterized by an excellent melting point and very good flow characteristics, which made it an outstanding candidate for additive manufacturing techniques. As a matter of fact, these kind of alloys are quite suitable, especially for laser powder bed fusion techniques like selective laser melting. During the manufacturing, using, for example, SLM, the rapid cooling allows to obtain a fine microstructure. This fine microstructure is usually characterized by a silicon network, which acts as a barrier to dislocations, so leading to good strength, maybe slightly limiting the elongation. In general, we know that when we talk about specimens or components which are made with these innovative additive manufacturing techniques, they are intrinsically subjected to the arising of defects and residual stress fields, which inevitably jeopardize the mechanical performances. So in literature, there are many works which explore and investigate how to enhance and improve the mechanical performances, taking into account the presence of defects and residual stress fields, especially in presence of fatigue loadings. All these works, for example, take into account the use of heat treatments rather than stress relief approaches for enhancing the mechanical properties, but the greatest part of them is focused on constant amplitude fatigue loadings. So one main criticality that we noticed is that in literature, there is a severe gap concerning variable amplitude fatigue loadings. For example, concerning the alloy that is under concerned and components made of this alloy through additive manufacturing techniques, there are only two recent works in literature, one published in 2023 and one published in 2024. That's why we decided to give it a go and we recently started an experimental campaign based on both constant and variable amplitude fatigue. So when we want to approach and tackle the issue of variable amplitude fatigue, we know that there is a clear methodology to follow according to literature. First of all, so first things first, we want to understand the constant amplitude behavior of a given material we want to study. The second step is the interpretation of the variable amplitude loading that we want to take in consideration. The following step is how to schematize this kind of load, because often if we want to carry out experimental tests, we want to simplify these loads by, for example, using counting methods. In parallel, we adopt a failure criterion which suits our needs. And finally, we compute the damage accumulation through famous and widely recognized rules. as I anticipated, focusing, for example, on the automotive field in which aluminum alloys are quite common and are widely used, in general, in this kind of field, the loadings are oscillating loads characterized by variable amplitude. And here there are just some examples of variable amplitude loadings which act on different components of a vehicle, for example. But in general, we can say that, that variable amplitude loadings, we know, may be classified into two big families. So we have block loadings, which are characterized by blocks identified by a given duration in terms of number of cycles and a given stress amplitude. If this duration degenerates in one cycle, then we have the one cycle block loadings, also known as random spectra. Among the hundreds maybe of loading spectra that are available in literature, one of the first that was introduced was the 8-block Gassner sequence. Gassner was maybe the first scientist who tried to approach the variable amplitude fatigue issue. And I'm taking this just as an example, as he was the first one to approach this problem. But we can say that starting from a variable amplitude loading, fatigue loading, we can always extract a cumulative distribution of the load. So this is just a way to represent our load based on the probability of exceeding a given stress amplitude. And then we can obtain fatigue life curves for variable amplitude loadings, which are called Gassner curves in honor of Ernst Gassner. And they basically are generalized Wheeler curves. So we know that if we have constant amplitude loadings, we can obtain the Wheeler curve. And in case of constant amplitude loadings, the distribution, the load distribution is a rectangular distribution. While if we have variable amplitude loadings, by applying the same sequence many times, in general, according to literature, from 5 to 10 times for achieving a service life load mixing, we can then obtain the fatigue life curve, which is the Gassner curve. So if we consider a general block loading characterized by blocks of different amplitude and duration, from the cumulative distribution, for each block, entering the Wheeler curve, we can obtain the number of cycles to failure, and then we can compute the Gassner curve. As often carrying out experiments with variable amplitude loadings is demanding, time consuming, in general is difficult, so Gassner curve can even be computed. So in this framework, we consider the completely random loading spectrum, which resembles a variable amplitude fatigue loading, which acts on a vehicle suspension. This loading spectrum was analyzed by through the rainflow algorithm. So we carried out, we extracted the rainflow matrix histogram. So through the rainflow algorithm, we are able to extract the cycles. So we know where each cycle starts and ends. And so for each cycle, we are able to compute its range and its average. And we plot these two quantities versus the number of cycles, and we obtain the distribution which is representative of the kind of loads that we are considering. And then we are able to plot the load distribution. This kind of load is what is called Gaussian loading spectrum. And for this kind of loads, if we use, for example, level crossing counting algorithm rather than range pairs counting algorithms, we obtain the same distribution. So the distribution is invariant respect to the algorithm that we choose. So now moving on to the case studies. As I anticipated, they were specimens obtained by selective laser melting made in this aluminum alloy, so aluminum silicon magnesium alloy. Here you can see a schematic of the specimen and a picture of all the printed specimens, so the actual ones. We carried out tensile tests for obtaining the yield stress and the strength. And then we carried out fatigue tests. So first of all, we carried out constant amplitude tests with a stress amplitudes comprised between 35 megapascals and 140 megapascals. Concerning the variable amplitude load, as I showed you in the previous slide, it was a completely randomic loading sequence characterized by a maximum load relative to a maximum stress of 420 megapascals. The loading ratio was 0.01 and the loading frequency 10 Hertz. Here you can see a picture of a specimen mounted into the instrument machine of our lab. And so I'm concluding, show you our very preliminary results because the experimental campaign just started. So in blue, we have the results for the constant amplitude test, while in red, the results for the variable amplitude test. We can see how concerning the constant amplitude test, so the Wheeler curve, the scattering is very limited. So the width of the scatter band is very limited as well. We can see how there is an abrupt change in slope in Wheeler curve in correspondence of the knee point, and this result is in accordance with the literature. Concerning Gassner curve, what we can say is that each point, first of all, is positioned on the plot considering the stress amplitude, which is relative to the maximum stress of the considered loading spectrum. In this case, results are a bit more scattered. We can see how the slope is less steep compared to the Wheeler curve. So at least at this stage, it seems that material is, let's say, less sensitive to this kind of loading. And we can assume that the Gassner curve or its eventual knee point potentially joins the Wheeler curve towards the high cycle fatigue part. So in conclusion, we know that aluminum alloys are used in several fields, especially in the automotive one, where oscillating loads are quite common, especially loads characterized by variable amplitude. As aluminum silicon magnesium alloy has good flow characteristics and an excellent melting point, is an outstanding candidate for laser powder bed fusion additive manufacturing techniques. But the main issue is that literature is still quite poor about the variable amplitude fatigue performance of this kind of material. And so we started an experimental campaign by testing specimens made in this alloy, with this alloy obtained by selective laser melting, subjected to both constant and amplitude fatigue loadings. And we started highlighting the different performances that this material has, but the experimental campaign needs to be widened, and it will be in the near future. That is all for me, and I really thank you for your time.